So in this lecture, we are going to discuss regarding the Bessel's equation. And a solution of Bessel's equation. So the differential equation of the form x square y double s plus x y dash plus x square minus p square y equal to 0, where p is greater than or equal to 0. It's called a Bessel's equation of order p. So this is known as a Bessel's equation of order p, where the value of p is positive. So here we have to find out what is the solution of this Bessel's equation. So I may write down as in one of the exercise that obtain a Frobenius series solution of the Bessel's equation and hence define the Bessel's function. The Bessel's functions are actually a solution of Bessel's equation of first kind of order p. So our objective is to calculate this quantity, okay, and to find out what is the solution for Bessel's equation. So let us see what are the regular singular point for this Bessel's equation. So consider the Bessel's equation. That is x square y double dash plus x y dash plus x square minus p square y equal to 0, where p is greater than or equal to 0 you have. To write down this is into the standard form, we can write this is as by dividing x square both sides. We'll have y double dash plus 1 upon x y dash plus x square minus p square upon x square y equal to 0. So hence here we have p of x. If you compare this equation with y double dash plus p of x y dash plus q of x y equal to 0. If I compare this differential equation with this one, we'll have p of x is 1 by x, q of x is x square minus p square by x square. And we note that this p of x and q of x are not analytic. At x is equal to 0. So this x is equal to 0 is a singular point. Now we need to check whether this x is equal to 0 is a regular singular point or not. For that I have to look at what is x into p of x. and x square into p of x. So x into p of x is equal to x into 1 upon x, which is 1, and x square into p of x will be x square into x square minus p square by x square, which will be x square minus p square. R analytic at point x is equal to 0. That we can see because this is a constant function and this is x square minus p square. So therefore, hence x is equal to 0 is the regular singular point. Since it is a regular singular point, according to the Fubini's method, we can able to write down a solution is of the form summation a n x raised to n y raised to n. So now, what is the identical equation we have? The identical equation of equation 1 is, what is the equation 1 that we are calling this is equation 1. What will be the identical equation for this equation 1? As per the formula, it is m into m minus 1 plus m into p0 plus q0, where what is p0 when you expand this x into p of x into the power series. So if I have this is into the power series, so I can write down that quantity here, x into p of x will be 1. So it is p0 plus p1 x plus p2 x square and so on. So this is the power series. So we can say that p0 is 1, and for q x square qx we will have it is x square minus p square. So it is minus, so I can compare with q0 plus q1 x plus q2 x square and so on. I can say that q0 is minus p square, q1 is 0, q2 is 1, and rest all other are 0. So here we have to write down what is p0 and q0. So therefore, this will gives you m into m minus 1 into m, the value of p0 which we have calculated 1, and q0 is minus p square equal to 0. So this is m square minus m plus m minus p square equal to 0. So hence it will gives you m square equal to p square. So this will implies m will be plus or minus p. So we'll have two values of m here. So here therefore m equal to p, or I can say m1 is equal to p and m2 equal to p are the roots of identical equation. And we note that this m1 minus m2 is 2m we have. Now we are looking for the solution, which solution is possible here. So now we solve this differential equation. We solve the equation 1 for the exponent m equal to p. So let y equal to x raised to m summation m running from 0 to infinity, n running from 0 to infinity, an x raised to n. This is the solution by Fubini's method we can say. where we are assuming this m equal to p. So that's why this is summation n running from 0 to infinity. An x raised to n plus p we have. I will call this as statement 2. And this is valid for some mod x less than r, where r is greater than 0. Now differentiating the second equation, we will have y dash, which is summation n running from 0 to infinity, an plus 1 an x raised to n plus p minus 1, and y double dash will be summation n running from 0 to infinity, n plus p into n plus p minus 1, an x raised to n plus p minus 2. So this is the value, these are the values we have, and we substitute these values y1, y double dash, and y into the equation 1, and then we are able to write down what is the recurrence relation of an. So substituting this all values in equation 1, we will have x square y double dash plus x y dash plus x square y minus p square y equal to 0. This is our equation 1. By x square y double dash x y dash and this x square y and p square y, and multiplying, opening out this bracket. So hence we have this. Now substituting the value, we'll have x square if I multiply to this y double dash here. So we can have it as summation n running from 0 to infinity an pn plus 1 pn plus 1 minus 1 x power pn plus 2, and plus summation n running from 0 to infinity. This x is multiplied to this y dash here. So that's why we can have this is summation n plus p an x raised to p plus n plus summation n running from 0 to infinity. Now it is y. So the y value of y is this plus x square is there. So it is into x square here. So here it is plus 2. So that's why it is an x raised to p plus n plus 2. And then lastly we have p square, which is n running from 0 to infinity p square an x raised to n plus p equal to 0. Now in this summation, if I want that everything is having the same factor or power of x, then I want to change this index of this summation. So for that I need to replace n by n minus 2. So let us write that by replacing n by n minus 2 in third summation. So in the third summation, we have to replace this n by n by 2. All other things will remain same. So therefore, we can have that is summation n running from 0 to infinity an p plus n p n plus 1 minus 1 x raised to n plus p plus summation n running from 0 to infinity an p n plus 1 x raised to n plus p. This quantity is exactly the same as which we have here. Now here there is a change. So instead of n, we have to replace n minus 2. So this n start with 0 here. It should start with 2 now. So that's why it is summation 2 to infinity a n minus 2 x raised to n p plus 1 minus summation n running from 0 to infinity p square a n x raised to p plus n equal to 0. Since this summation is starting from 2, I need to change all the index with that. So for that, we'll write a separate term for 1, 0 and 1. So therefore, this is equivalent to write down when n equal to 0 here. This is p into p minus 1. The coefficient is x raised to p, a0. Here is also x, a0 into p, x raised to n is there. So for that, the coefficient is plus p. Then the last term will contain that term. So that will be p square. A0 into x raised to p is common out. The next term is of x when I have n equal to 1. So this is a1. So the coefficient will be a1 x raised to p plus 1. So here the coefficient is p into p plus 1 because this I replace n p n equal to 1. This is 1 minus 1. So it cancel out. So it will be p into p plus 1. Here we will have p plus 1. And in the last term also we have p square. Now the rest of the things as it is. So that is n running from 0 to infinity. An, I'm just writing the terms of an separately, or I can write down all the terms which having x power n plus 1 together. So it is an p plus n, p plus n minus 1 plus p n plus 1 minus plus 1 minus p square an x power n plus p equal to 0. Now if you compare the coefficient both sides, or first you just simplify what is this term. If you don't want to write down, it is better to compare the coefficient both sides. So equating to 0 the coefficient of different powers x we get. So the first one is the
Sir, an minus 2 वाडू term.
रही गई यहाँ 1 ની જગ્યા પર en minus 2 આવશે. That term is there. Yeah, this one. So when you substitute this first one, let us see what is this quantity. This quantity is actually, if I simplify, then this is p square minus p plus p minus p square. So that will get cancel out everything. So this quantity will become 0. What will happen here? We'll have this is p square plus p plus p plus 1 minus p square. P square will get cancelled. So this is 2p plus 1 into a1. So this is gives you 2p plus 1 into a1 equal to 0. But this will implies a1 equal to 0. Why? Can somebody give me answer to that? Why the A1 is 0? Because your P is greater than or equal to 0 as per your assumption into the Bessel's equation we have taken. Your P is greater than or equal to 0. And here in this expression, you will have P equal to minus 1 by 2. So there will be two possibilities, either this is 0 or A1 is 0. But P will be always positive. So that means this will give you P equal to minus 1 by 2, which is not possible. So hence A1 is 0. And the last term what we got, let us write down that we have it is Pn plus 1, sorry, P plus n, P plus n minus 1 into An plus P plus n, An plus An minus 2 minus P square An. So if I can simplify this quantity, then let us see what is the things we have. This is equal to 0. So that will gives you An minus 2 equal to all the things. If I take on the other side, this is P square. I take common An from each of this. That is P square minus P minus n. If I take this one on the other side, P square minus P square goes on the other side. And then it is minus P plus n, P plus n minus 1 into An. So now let us look at this situation or this expression. What will be this? So if we can take common out from this two, Pn plus 1, then you will have this expression is P square minus P plus n is common from this two. Inside bracket, left is 1 plus Pn plus 1 minus 1 into An. And this 1 and 1 cancel out. So finally you will have it as P square minus P plus n whole square into An. So therefore I can write An equal to An minus 2 upon. This is also further simplified, that P square minus 2 np plus, sorry, minus n square. So this is get cancelled out. So this is we got minus of, if I take n common from this two, and this is minus of n into 2p plus n, where n is greater than or equal to 2. If I call this is a recurrence relation 3. And this is a recurrence relation of equation 3 or equation 1 we have. We can write this is the recurrence relation of equation 3 we have. Now let us see what are the values of this A2. See, we already have the value of A1, which is 0. So let us see what are the values of A2, A3. If I substitute n equal to here. So hence now putting this value n equal to 2. If n equal to 2, then it is a2 equal to minus a0 upon, because this minus sign I take in the numerator, n equal to a2, 2 into 2p plus 2. So it is 2 into 2p plus 2. That I can write down as minus a0 upon 2 square. If I take common 2, p plus 1. Now put n equal to 3. A3 will contain minus a1 upon 3 into p, 2p plus 3. 3 into 2p plus 3. But we already have calculated that a1 is 0. So that's why this quantity will become 0. Put n equal to 4 in that equation. We'll have a4, which is minus 2a2 into 4 into 2p plus 4. So this will be minus a0 upon minus minus become plus, because the value of a2 we can substitute, and this will become plus. This is already 2 power 2 is there, and 2 is common from this. So this is 2 power 2, and this 2 power 2 will become 2 power 4. And here I take common 2, and this p plus 1 and p plus 2 is already there. So we'll have this is the expression. Now putting n equal to 5, we observe that a5 is 0 because a3 is 0. And putting n equal to 6, we'll have a6, which is minus a4, 6 into 2p plus 6. Then if you substitute this a4 value, which is positive, so this is negative, so it will be gives you a0 upon of minus sign. This is 2 raised to 4 is there. This is 2 raised to 6. So combinedly, you can write down that is as, and 2 is common from this. 1, 2 is coming from here, 1, 2 is common from there, so it is as 2 raised to 6. And 3 is there, is left because 2 3s are 6, and this 2 is already there. So I can write this is 1 into 2 into 3. And then here inside bracket it is p plus 3 left. So it is p plus 1, p plus 2, p plus 3. So now we can see the things, or we can have a, and in general we can write down in terms of a0, which is even. For odd, all of them are 0. So if you substitute this value of a0, a1 and so on into the solution, so substitute these values to expression 2, we have y equal to summation n running from 0 to infinity an x raised to n plus p. So this is equal to x raised to p is common out, a0 plus a1x plus a2x square up to so on. So hence we have, this is the expression x raised to p, a0, a1 is 0, so I'm not writing that, a2 is we got minus a0 upon 2 square into p plus 1 x square. So we can see that a2, the value of a2 is this. Then it is a3 will be 0. Then we'll have next value is a4, which is of positive sign, a0 upon 2 raised to 4 into 2 factorial p plus 1 p plus 2 into x raised to 4. The next term is 0 for a5. Now a6 or a6, the value of a6, we will have minus a0 upon 2 raised to 6, 3 factorial p plus 1, p plus 2, p plus 3, x power 6, and so on. So this is the expression we have for y. And if you can write down this is in terms of in the summation notation, then this a0 is I take common now. X raised to p is already common. Summation n running from 0 to infinity. Then it will be have minus raised 1 raised to n because it is of alternating sign. This is 2 raised to 2, 2 raised to 4, 2 raised to 6. So it is 2 raised to 2n. And it is 1 factorial, 2 factorial, 3 factorial. So it is n factorial. P plus 1, P plus 2. So it is adding the that many terms. So this is x, sorry, P plus 1, P plus 2 up to P plus n into x power n, 2n is there, which is required solution of Bessel's equation. Now the question is to calculate other equation, that is we will do it later on, but before that the question was to define what is Bessel's function. So this is exactly the Bessel's function is. This function which we have here, it's known as a Bessel's function. So let us define what is Bessel's function. The definition of Bessel's function of first kind. Of order P. So Bessel's functions of first kind of order P. So the definition is stay like this. Bessel's function of first kind of order P is denoted by Jp of x and defined as a particular solution of Bessel's equation. As I told you, the Bessel's functions is exactly the solution of Bessel's equation by taking the value of a0 is equal to 1 upon 2 power p into p factorial into that last expression which we have here. This is equation 4. So in this expression, the particular value of a0 if we pick, that is a0 is equal to, we will pick this 1 upon 2 power p into p factorial. So thus, this Jp of x is x raised to p upon 2 power p into p factorial summation n running from 0 to infinity minus 1 raised to n upon 2 power 2n n factorial p plus 1 p plus 2 up to p plus n into x raised to 2n is there. But what is this gives you p factorial into p plus 1, p plus 2 up to pn, p plus n. So it is exactly 1 into p into 1 into 2 into 3 up to p, and then p plus 1, p plus 2, p plus n. So this expression I can write down summation n running from 0 to infinity minus 1 raised to n upon n factorial is there, n plus p factorial, because this is n plus p factorial together with this one, and this n factorial is already there, and this divided by 2, and this one, and this whole quantity I may write down as x by 2 power 2n plus p, that is the power of x, and the power of 2 is 2n plus p here is also there. So that's why it is 2n plus p is there. And we call it, this is expression 5. And which completes the objective which I have started with, that define the Bessel's function of a first kind and also solve the Bessel's solution of the Bessel's equation. If you have any doubt, you can ask related to this.